Okay, so we talked about planar graphs and embeddings, talked about embedding graphs in the plane and in the sphere, and we kind of showed, well, because of the stereographic projection, doing one would be the same as the other. And so we kind of just fixed ourselves looking at the plane. And I did mention that K5 and K through 3 are going to be important examples of non-planar graphs. So remember, planar, there's a fancy topological definition here, but what you're trying to do is draw the graph in the plane such that there's no crossings over these edges. You don't want two edges to have to cross each other. Okay, they should only meet potentially if they have vertices that they share. Okay. Is that okay? The topological definition is you kind of have an equivalence class of drawings, and they're equivalent if you can kind of like move things around. So there is a topological definition to that, like continuously moving things, right? Yeah, if any of you have seen topology, then maybe that makes a little bit of sense. Then we talked about, okay, once you have a planar graph, then we can actually define regions or faces of the graph, okay? And if you draw it on the plane, you'll always end up with an outer region or an outer face. But if you do that on a sphere, there's no such thing because I can actually move regions around, and there's no real way to define that. And we talked about boundary of a region, and then the important theorem that we proved last time was Euler's identity, okay? So this one says, if you have a connected planar graph, then the number of vertices minus the number of edges plus the number of faces or regions must be fixed. It must always be 2, which is quite significant. So that's actually telling you that there's well, there's a really nice relationship between all those parameters, right? So, and you can prove it for the general case that it's disconnected, but it's still planar. And you just, instead of being 2, it'll be 1 plus the number of connected components. Okay, so that's where we left off. And today I want to talk about Kuratowski's theorem. So what we're trying to get at is something similar to what I mentioned with line graphs. Do you remember that we effectively classified line graphs? A graph is a line graph as long as it doesn't have some induced subgraph that's in this forbidden list, right? We're going to actually have a very similar theorem. We're going to have a theorem that says graphs are planar as long as they kind of obey these simple rules. And there is going to be a couple of forbidden graphs, which are those 2 that I just showed you, the K5 and the K33. But I kind of have to make sense of what are these substructures that we're talking about, because it's going to be a little more general. Okay, so in order to do that, I have to define a couple of things. So first, what is a subdivision of a graph? So a graph H is a subdivision of a graph G if either they're isomorphic, so I didn't really do anything, or H can be obtained from G by inserting vertices of degree 2 into the edges of G. So let me kind of just show you what a subdivision is really doing. So let's say that I have this graph, G. Okay. So let's draw some subdivisions. Okay. Well, one subdivision I can draw is this, which is exactly the same. Okay. So this is that's a trivial subdivision. Another subdivision, what you're doing by subdividing an edge is you're sort of just inserting a vertex of degree 2 along an edge. So pick any edge that you want. I'm going to pick this one right here. And then you insert a vertex right here. And by doing so, you're actually you're increasing the total number of edges by 1. Right? And you're increasing the number of vertices by 1. Okay, so you get these 2 new edges and this vertex that's pretty much at the center. Okay, so you're kind of like splitting this vertex. That process is reversible. It's usually sometimes it's called a smoothing an edge out. So if you happen to have a vertex of degree 2 like this, you can smooth it out by kind of just getting back to this process, getting back to the original edge that you had. Okay, so I could add a vertex there, and I could add one here. Okay, so this is an example of a subdivision. So you see you're inserting vertices of degree 2 into the edges of G. So we call this H2. Now, the thing that makes some subdivisions not easy to detect is because you know that graph isomorphisms give you some wiggle room, right? So by adding that in, I actually now have a 4 cycle, so I could redraw this. I have that 4 cycle up top, and I still have this 3 cycle here. And then now I have sort of a longer path, right? So you see, effectively what you can do is you can bump up the size of cycles as well with sort of this process here. So this is also H2. And another example that we could draw is, well, I could bump that thing up to be maybe a size 5 cycle, right? And I could bump this up to a size 4 cycle, and then I could increase this length as far as I want, really. So this is another subdivision. Okay. Maybe you might want to draw some intermediate step to see that, but do you guys kind of see, I can grow a cycle by inserting vertices of degree 2. So I can bump up the size of that cycle, and this triangle, I can add another vertex of degree 2, bump up the size of that cycle. And because I can insert these degree 2 vertices anywhere, I can actually increase the length of any sort of path component of the graph, right? Is that okay? Okay, so an observation, a subdivision of a graph is planar if and only if G is planar. So if G is planar, by inserting these vertices of degree 2, I'm not going to actually increase any crossings in the graph, right? Do you agree with that? Like if I start with this guy is planar, right? So if you start inserting vertices of degree 2, are you actually inserting any crossings into the graph where edges have to cross over each other? No, because you're just inserting a vertex where there already was an edge. So you're not increasing the number of crossings. Now, if you redraw it, you can, of course, redraw it in a way that you might have crossings, but that's not what you're answering with planar. The planar is there an embedding or a drawing such that there are no crossings, right? So this direction is not too bad, going from planar to seeing that the subdivision would be planar. But what about the other way? So if you had a subdivision that's planar, well, to get back to G, the process is reversible. You can smooth out these edges. Anytime you encounter a vertex of degree 2, I can effectively remove it but maintain that connection. And that process also is not increasing the number of crossings in the graph, right? Do you agree with that? So the intuition of this observation, it's really not even, that's why I kind of would call it more of an observation rather than a proposition, because it's not even really that crazy of a result. Okay, so last time I mentioned K5 and K33 are not planar. We haven't actually proven that yet, but I promise you we will prove that. We're going to use some other tools that'll help us. And you don't actually need to use those tools. You can prove it by brute force. You can just sort of sit down and combinatorially argue why there actually will have to be a crossing in that graph. But the proof will be much shorter if we have some additional tools. Okay. So recall that these two are non-planar. So what that means is any subdivision of those two would also be non-planar. So that's kind of nice. So that gets us somewhere. Maybe we can build non-planar graphs using them. But what's actually interesting is this is not only a necessary condition, but it's actually sufficient as well, which is what the Kuratowski proved. Okay. So a necessary condition for G to be planar. So a graph G is planar only if G contains no subgraph that's a subdivision of K5 or K33. So the proof of that is pretty short. So just the necessary part. Suppose G contains a subgraph that is a subdivision of K5 or K33. Well, by our observation up here, because those guys are not planar, then the subgraph cannot be planar. Therefore, if you have a subgraph component of the graph that's not planar, then the whole graph is not going to be planar, right? If you prove a portion of the graph has to be non-planar, if you add more stuff to it, it's not going to make it's going to make it worse, right? Not better. Okay. In fact, you might actually be requiring even more crossings. So that's a completely separate question. Okay, but what's amazing is that that's also a sufficient condition. So a graph is actually planar if and only if G contains no subgraph that is a subdivision of K5 or K33. Right? So this right here, this process, and an even more general version that I'm going to show you in just a second, is sort of an extremely useful way for identifying non-planar graphs. And also such subgraphs can be found in linear time. So if you guys know about big O, so big O of n as measured by the order of the input graph. So the running time increases at most linearly with the size of the input, which is very fast, okay? Now, you might ask, okay, well, if it's that easy to detect, are planar graphs even useful? Well, you could think of them as, a lot of times if you're trying to build some kind of algorithm, you could test it on a family of graphs that at least might be useful. So one type of graph that a lot of people will test on is the planar graphs first, and then they'll see if they can generalize it to more general structures. If you want to know an actual nice application of planar graphs, other than perhaps there's some geometric results here that we'll talk about later on. There are some nice geometric implications. If you were going to design, say, a circuit board, right, and you wanted to minimize the number of possible crossovers that you had to have, trying to figure out if that structure can be drawn in a planar way would be very effective, right? A very useful technique. Another way of answering that is like, how many levels do I have to add? Because if you let's say you're required to add a crossing into the graph, you could add a level. You can add a level, and you could have one edge go up to that next level, move around, and then go back down. Now, if you have to add levels, you almost have all the freedom you need, because if you can draw a graph in 3-dimensional space, you can always draw a graph with no crossings in 3-dimensional space if you think about it, because just arbitrarily put your vertices wherever you want, maybe just say that they're in fixed space, and you can draw your edges using continuous curves through space. So there's no way that you're going to have those things cross. Right? If they were like connected by maybe surfaces or planes, then they might have to cross. But if you're talking about being in 3-dimensional space and connecting 0-dimensional things with 1-dimensional things, there's not going to be a requirement that they cross anywhere. It's only when you run into the sum of the dimensions being equal to the outer space. Like if you have planes and lines, they might have to cross, right? Because the dimension of that would be 2 plus 1. Or planes and planes, then they will definitely have to cross, unless at least if you're talking about them going through, say, the origin. If they're affine, then they could be parallel planes. But all right, now we're kind of getting off subject. But hopefully you see that that's kind of you pretty much have classified planar graphs. Okay, and not only did you classify it, it's actually not that complicated, right? It's not like I'm saying it's got to be K5, K33, or a list of 500 forbidden graphs. There's only like 2 forbidden graphs. But the only requirement is that we have to deal with this subdivision question. So maybe there are other processes that we could use other than subdivision, but there might still, we might be able to still detect whether or not the graph is planar. Okay, so that's what the next note set is on. So this is Kuratowski's theorem. Okay, so this was the first one that had to do with the classification in terms of sort of, you have these forbidden, they're not necessarily subgraphs or subdivisions, but so you don't want a subgraph that is a subdivision of these. Okay, so the next node set. Did everyone get the next node set up here? Okay, so graph minors, that's what we're going to talk about now. Okay, so we kind of have already talked about contracting an edge, but the version that I told you was actually a little bit more general. Do you remember when we were contracting an edge when we were talking about labeled trees, right? And labeled spanning trees and things like that. Okay, so if 2 adjacent vertices U and V in the graph are identified together, then we say that we have strictly contracted the edge EV. So let me sorry. Yeah, let me just draw some example for you here. Okay, so let's say that we have this graph. Okay, so let's label this T, U, V, W, X, Y. Okay. So what I'm gonna do here is I'm going to strictly contract U and V together. Okay. So if two adjacent vertices U and V in a graph are identified, then we say that we have strictly contracted the edge. But you can actually do a strict contraction even if they are not adjacent to each other. So maybe first I should just show you an example where they actually are adjacent to each other. Okay, so let's draw that first. Okay, so let's say I have U, V, and W here. Okay, so if I strictly contract U and V together, you would actually end up with this graph. So you can think of that new vertex as UV. Now before, so this is strict contract U and V. Okay, you would get this. Now before, when I originally showed you contraction, I said you would identify them and you would not actually be getting rid of any edges. So you would actually end up with a loop there, right? So the strict contraction, you want to actually end up with a simple graph in the end. So what you're actually going to end up doing is you're not going to have any loops or multiple edges anymore. So you kind of just think of it as you're contracting along that edge and you produce this graph here. Okay, so this is an example when they are adjacent, but you actually can also strictly contract U and V in this situation as well. So let me show you what the final result would be. Okay. So if I strictly contracted U and V together, it looks like I would end up with these multiple edges that are created. Do you see if I identify those together? It looks like this edge and this edge would follow it, and I would sort of have two edges here and two edges here. But when you're doing a strict contraction, you want to end up with a simple graph in the end. So you're gonna effectively identify those edges. So, or you can think of them as just deleting the multiple edge situation. So you'd actually just end up with this. Okay. So this is what would happen if you kind of identify U and V together. Okay. So this is strictly contracting U and V, and note the graph remains simple. Okay. In the literature, most of the time, this process is actually what people are referring to when they are talking about a contraction. Okay, so they don't even say the word strict. What we kind of did before was a more general version of a contraction. I guess you could actually call this one a contraction and maybe that one a weak contraction or something like that. Okay, so just note in the literature, they might not always use the word strictly contracted. Most of the time, they actually mean this. So if you want to think of there being an intermediate step between these, would it be helpful if I just, so strictly contract U and V. Okay, if you want to think of there being an intermediate invisible step between these two, what would the graph look like? Well, if I just identified those together without deleting any edges, right, it would actually look something like this. You guys kind of agree that if I identified these together, then I would still have this edge and this edge. So the picture would kind of look like that. But because this resulting graph is not simple, we are not going to allow these multiple edges. So that's why you can think of it as either identifying them together or actually deleting the extra. Okay, so we still have like U is equal to V here, right? Or just, you could call it either UV or just call it U or V, it doesn't really matter. Okay. Is everyone okay with that? It's probably a little easier to think of them when they are adjacent, because if they're adjacent via some edge, you can just think of it as combine and then delete the loop. So the intermediate step here is there would actually be like a little loop around that one. Any questions? Contraction is usually a little bit weird, right? Deleting is very easy, right? Just delete stuff. But contracting is a little bizarre. Okay, so what is a minor of a graph? All right, now, so a graph H is called a minor of G if they're either isomorphic, so you didn't actually do anything, or the graph isomorphic to H can be obtained from the graph G by contractions, deletions and contractions effectively. Okay, so edge contractions, edge deletions, and vertex deletions. So when I write this, we're actually talking about these new strict contractions, but in the literature, usually they're not going to add that word strict. Okay, so this is the type of contraction that they're talking about. Okay. So a nice summary of this, because you're allowed to say edge deletions or vertex deletions, and you can do them in any order that you want, it's much easier to just say that a minor of a graph is just, you start with a graph and just do any number of deletions and contractions that you want. Okay, a graph that's obtained by deletions and contractions. That's probably the fastest, you know. In other words, a graph obtained by G via deletions and contractions. That way, you're kind of taking care of, oh, are you talking about vertex deletions or edge deletions? Either one, doesn't matter. Okay, you can actually more generally define this thing, and you can actually just do it by successive edge contractions, because if you're just talking equivalently, a minor is either it's isomorphic or it can be obtained from a subgraph of G. So if you're talking about a subgraph of G, you're already deleting vertices and edges, right? Okay. So you could just think of it that. So obtained from a subgraph of G by a succession of contractions, because that's the only one that you're not going to necessarily end up with a subgraph of the original one. Sometimes you will. Like, for example, does everyone agree that if you properly, like if I did call this, instead of UV, if I called it U equals V, right? So if you say U equals V, and now your vertex set, you think of it as a new set, and you're replacing U and V, just delete one of them, right? Would this be a subgraph of this structurally? The answer is yes, right? But in general, that's not going to happen if, say, you were to contract along a cycle, right? Do you guys agree if I had a 5 cycle and I contracted one of those edges, I'd end up with a 4 cycle, right? And that 4 cycle is not a subgraph of the original one, right? A 4 cycle is not a subgraph of the 5 cycle. Does everyone agree with that? Or am I making this more confusing than it needs to be? Like, for example, okay, here's a 5 cycle. Do you agree that I could identify these two and I would get a 4 cycle? Okay, so this is a minor of the original graph. Okay.
So what if you delete the original connection?
Sorry? Say that again?
Like you deleted an edge, so you kept that.
Yeah, but see, well, yeah. So when you do contractions, right, the intermediate thing that you would actually have looks like this. Okay. When I connect those. Okay. This is a minor of G, but not a subgraph of G. So all I was just pointing out is if I took an edge and I deleted it, that would be a subgraph, right? Right? G delete E. Does everyone agree that this is a subgraph of the original? This one's a subgraph of this, right? Right? But this one is not. Does everyone agree that a 4 cycle is not a subgraph of a 5 cycle because, well, I need to be able to have the vertex set as a subset, which you could claim that's true, right? Because you could call this new vertex in the vertex set either U or V, so that's fine. But the problem is that the resulting edges are not, it's not correct anymore, right? Because, for example, I don't have the edge that goes from U to this vertex in terms of the same exact definitions that I had before, okay? So it doesn't satisfy the definition of a subgraph before. So that's why we have kind of this new structure, which we're going to call the minor. So a minor is something that is obtained by deletions and contractions. So this is a subgraph of G, and this is also a minor. So does everyone see that minors are sort of like a larger structure that you can, all subgraphs should be minors, right? Because a subgraph can be obtained by deletions, but not all minors are subgraphs. Does that kind of make sense? So if you like Venn diagrams. We okay with that? Yes, yes, yeah. Because they structurally have more to satisfy, right? Whereas a minor, what we were kind of saying is to simplify the definition of minor, so you could say that you can obtain it by deletions and contractions, but you can equivalently just say, okay, I could actually pick any subgraph that I want and do any contractions that are necessary. Yeah, okay. Like for example, this is U and V, right? Can I get to this? Just contract them, right? Okay. Now the weird thing is yeah. All right. I think we're kind of making things more confusing, but the only thing I was just trying to point out is, do you agree when you contract, you're not necessarily going to get a subgraph of the original by our original definition. Okay. Okay. But that's why we need this new structure of a minor, which comes about via once you start talking about contractions. Okay. Now, if H is not isomorphic to G and H is a minor, then we call it a proper minor of the graph. Probably would have guessed that. Just like before when we said proper subgraph. Okay. Now we can say a theorem, okay, which is even nicer. So Wagner's theorem. Okay, we'll get to that in just a second. So if G is a subdivision of H, then H is a minor. Okay, so that's one theorem. So this is relating subdivisions to our new structure of being a minor. Okay, the converse of the above statement is not always true. So see if you can prove that. So if H is a minor, then it's not necessarily going to be a subdivision. Okay, but if you take a graph and you subdivide, let me show you an example of this just real quick. So if I take this graph and I subdivide, let's say that I add this vertex here. So now I'm going from a 4 cycle to a 5 cycle, right? So this is saying if G is a subdivision of H, okay, so G, this is H, right? So this is a subdivision of H. Do you agree that H is a minor of G? Can I go back? Couldn't you just contract these two vertices and you get this 4 cycle back, right? So that's the same picture that we had before. So if I add these vertices of degree 2, then I produce a subdivision of H, and I can go back by contraction, right? I also said that you can go back before, you can undo a subdivision by what's called a smoothing, but to get a minor, how do we get a minor? You have to either delete or contract, right? So I have to be able to get back. I can't get back by deletions alone, right? I need that contraction. So does everyone agree that I could contract to get back, right? Thus, H is a minor of G. Okay. The converse is not going to be true though. If you have something is a minor, then it's not necessarily possible to get G by doing subdivisions. Okay. See if you can come up with a counterexample to prove that. Okay. Remember, subdivisions, what are you doing? You're just taking an edge and adding a vertex of degree 2. So if you come up with a clever minor that is not just undoing that process, then you'll probably get a nice counterexample that way. Okay, so now by Kuratowski's theorem, we can immediately say the following. So if G is non-planar, then K5 or K3 is a minor of the graph. Okay. So Wagner actually proved the converse of this is actually true. And therefore, we get another characterization of planar graphs. So let G be a graph. If G has a K33 minor, then G contains a subdivision of K3. And therefore, if G contains a subdivision of K3, I hope I said 3 both times. So if G has K33 as a minor, then G has a subdivision of K33. And therefore, by Kuratowski's theorem, it would be non-planar, right? Because Kuratowski says if there's a subgraph of G that has a subdivision of this, then it's not planar, right? And if G has a K5 as a minor, then G contains either a subdivision of K5 or a subdivision of K33, which therefore would also mean that it's non-planar by Kuratowski's theorem. Okay, so that's why Wagner's theorem comes later, because he kind of builds off of Kuratowski's theorem, but he creates this more general characterization, which is actually in a sense much nicer because you're able to do more operations. You see, not just subdivision and looking at the subgraph. You can now do deletions and contractions and get this. So it'll be even more useful to us. Okay, so a graph G is planar if and only if neither K5 nor K33 is a minor of the graph G. Okay? So let me show you how useful this is. First example, let's look at the Peterson graph. So example, the Peterson graph, P is non-planar. Okay. So let's draw the Peterson graph. Oops. So remember, draw your star and then the edges here. Okay. Do you, if you stare at this, can you think of a clever way to, in the way that that's drawn, can you think of a way to delete or contract edges and vertices if you want? So deletion, via deletions or contractions, can you produce either a K5 or a K33? This kind of looks like a K5, doesn't it? K5 is a pentagon with a star. So if I could just make the star go out here, then I'd be done. Do you see that if I just contract, 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 what do you get? Does everyone agree that if you contract, you will get this, which is isomorphic to K5. Okay. And therefore, by Wagner's theorem, this right here is now a minor. Do you guys agree? Because I produced it via contraction. So K5 is a minor of the original graph. Therefore, the original graph is non-planar. Kind of cool, huh? So Wagner did all the difficult work because if you kind of think about it, he essentially showed the connection between minors and these subdivisions. So he in his proof, well, let me give you a second. Everyone write all this. I'll go back. I just wanted you to see right here if G has K5 as a minor. So that's the situation we're in, right? And Wagner proved that G would contain either K5 as a subdivision or K33 as a subdivision. So somehow he knows that if you could do this process, then this original graph actually has to have K5 or K33 as a subdivision for its subgraph. So he did all the heavy lifting for you. He tried to prove that you could use Kuratowski's theorem to prove the non-planar. So you kind of see he did all the heavy lifting to get these structures to give you the subdivisions. Okay. And now that you can do deletions and contractions, that's much more intuitive. I think your brain is much better at doing things at identifying minors because you just have to do deletions and contractions. Whereas subdivisions, I mean, it's harder to recognize them sometimes, but it's not terrible all the time. I don't know. Maybe some of you are better at the subdivision route. So if you're better at that, then just do Kuratowski's theorem. But most of the time, you're just going to use Wagner's theorem. I think there's going to be one homework assignment where I just ask you to use one or the other, or maybe there's one type of graph you could use both if you want. Okay. And the whole point of that is to kind of get used to what you're actually doing with these operations. Any questions of that? So that's pretty quick, right? In general. That's much better than doing this by brute force, right? You're just doing some simple graph operations and getting to one of these sort of forbidden graphs. Okay, now other directions you can take the theory that we're not going to really explore in this class, but you might find interesting if you like this planar graph stuff. Okay, there are things called outer planar graphs. You could look at planar graphs and whether or not they contain Hamiltonian cycles. So there might be specific applications of this. I think outer planar are planar graphs where all the vertices actually have to be on the outer face. So you can't have vertices on the inner face of the graph, right? If you draw a planar graph, so this graph, do you see all the vertices are on the outer face or on the outer face? I think that would be considered an outer planar graph. So not all graphs are outer planar. Not all planar are outer planar. You can draw.
Kind of like everything's connected to the exterior region, right?
All the vertices, yeah. And there's a classification for outer planar too. And they have their own types of applications. But this is something else you could look at. Something you might be interested in is this crossing number, because in a lot of applications, you might want to figure out what's the minimum number of crossings that the edges would produce and among all the drawings in the graph. So that's a very, in general, kind of a difficult question because you're looking at all the drawings. So you're looking at all the things in this equivalence class and you're trying to figure out the minimum number of crossings. Now, there are some bounds for the number of crossings that are somewhat nice, but they're not always really good. Okay, it's nice in the sense that it involves simple parameters. This one only involves n and m. Okay, so you have a bound for them. And then people started to look at what's crossing numbers for specific families of graphs. So for the complete graphs, you can come up with a lower bound for the number of crossings. And for the complete bipartite, where you allow the partition set sizes to be different, right, S and T, there is a bound for this as well. Okay. but I'm pretty sure that there's still a lot that's unknown about that in general, because it's kind of a difficult question to solve. Okay. Another thing that you might find interesting is, so far we've only been doing embeddings in the plane, right? And we showed that that's the same as embedding in the sphere, but you can do things a lot more general than this, where you can embed in on a surface that has a higher genus. I don't know if you guys, so for example, so a torus, it's like a donut. Okay, you guys have seen this before? So a torus, right? So this has genus equal to 1. So a sphere has genus equal to 0. So the genus is kind of like, how many holes does the surface actually have through it? So a donut kind of has this one hole here, okay? And what you could ask is, okay, if I cannot embed on the plane or the sphere, so it's a non-planar graph, when you add, if you ask, can I embed the thing on a torus, because you have this hole in the surface, it actually gives you more wiggle room to where you could take those edges, and you might avoid crossings actually. Okay, so for example, let me just show you two different embeddings of, say, K4. So K4, I can definitely embed on this torus, right? I can embed just the normal way. Here's K4 embedded on the torus, okay? But here's a different embedding, okay? So here's a completely different one that's unique to that one, okay? Let's say that I have my 4 vertices like this, okay? So the missing crossings that I have is I could go across this way, but instead what I'm going to go is around the back. Okay, so I'm going to go around the hole in the torus this way, okay? And then this edge, I'm going to go all the way around the torus this way. And do you agree that there's no crossing there? Because this edge is behind, it's on the other side of the surface. See that? So I still have no crossings, but this is a completely distinct embedding. So here's a different embedding of K4 on the torus. Now K4 was planar, right? I just drew it on a sector of the torus that I could sort of, I really didn't need the hole in that surface, right? But what do we know is not planar? K5 and K33, right? So here's a good challenge for you. Can you, well, maybe I should spoil it for you, because, well, I told you I'd let you go. But see if you can embed K5 or K33 on the torus. And you can do both of those. So see if you can do it. So an interesting question might be, what is the minimum number of holes that I need to embed my graph? All right. Maybe I'll mention what's going on here next time. Okay. So on Friday. Okay. So that's a good challenge problem for you. All right. I'll see you on Friday.
That was like a good metaphor for like a contraction.
Yes.
One of those like chain door locks.
Yes.
You think of that,
Yes,
like
yes,
that,
yes.
Like 2 vertices. And you bring
Yes.
together, you got that loop.
Yeah, that's a good point. Yeah. And then you just get rid of the loop, right? Yeah. So the old way we contracted, yeah, you would keep that, but
Yeah.
This is where they, use the chemistry of wedges and dashes.
sorry?
This is where they use chemistry wedges and dashes, because dashes are in the page.
Oh yeah.
Yes. Oh yeah, that's right. That's right. Yeah.
So you can just draw like a wedge symbolizing inside of the page, actually.
Uh-huh.
I don't know if they use that notation, but that's for chemistry, they should probably use it in one.
Yeah. You can, there are ways that you can draw that on the plane and then say that you're identifying the edges together, the edges of the page together in such a way that you're producing a torus too. But that actually kind of makes some of the drawings a little more complicated.
It kind of reminds me of like not theory almost.
Oh yeah, yeah.
It's like, and behind them. Is there like a relation like between like knot theory and like a genus? Like does knot theory have like genus like one because it's like a torus and one
Well,
go behind it?
A knot in general is you are trying to figure out
Something minimal amount of
have it going. Yeah, well there it's like there's no
I like when I was at Alfred, someone took like that